welcome to the series of instructional videos for the third year Analytical Chem Labs. I'm Dr. Robin Studley, and this video will be about the instrumental setup for ion chromatography. The instrument that we're looking at today is the Metrome 883 ion chromatograph that we have set up for anion analysis. What we see today can be generally applied to other ion chromatograph systems. The ion chromatograph consists of an eluent pumping system, injection port, column, suppressor, and detector system. We'll first start off with the mobile phase, otherwise known as the eluent. The eluent we use is a carbonate-bicarbonate buffer. It's carried throughout the instrument using a pump. A carbonate-bicarbonate buffer is used because it gives pH control and the total ionic strength can be easily modified. Once the eluent is flowing throughout the instrument, the sample is introduced. The analyte is introduced into the sample loop by suction. Use of the sample loop allows for reproducible sample volumes. Once the position of the loop is switched to the inject position, the mobile phase is directed through the sample loop, thus carrying the sample to the column. Often, a guard column is placed before the analytical column. The guard is a short section of column similar in composition to the analytical column. It filters out particulates and strongly binding contaminants that may never release from the column material. This allows the much more expensive analytical column to have a longer life. Separation of the sample's components is achieved in the analytical column. The components are separated based on their relative affinity for the stationary phase compared to the mobile phase. In this case, the stationary phase inside the column is a resin that has been bonded to aminated latex beads. The functional groups bonded to the resin are positively charged in order to attract the analyte anions. The eluent also interacts with the stationary phase. However, this interaction is minimal or up to equal to that of the sample interaction. The positively charged sites on the surface of the stationary phase are initially balanced by bicarbonate anions that are loosely bound through electrostatic interactions. However, as the sample enters the column, the analyte displaces the bicarbonate anions and is retained on the stationary phase, as it usually has a higher affinity for the stationary phase. This is like an equilibrium process, meaning that the analyte competes with the buffer but doesn't permanently displace it. If the analyte binds more strongly, its solution from the column can be sped up by changing the proportion of bicarbonate to carbonate or using a higher ionic strength eluent. After the column and before detection, the separated species and eluent reach the suppressor. The suppressor in this case is a cation exchange device. The function of the suppressor is to reduce the background conductivity of the eluent and increase the sensitivity for the analyte ions. The suppressor uses a regeneration process which is carried out in 3 steps. The first step in the process is where bicarbonate and carbonate anions are converted to carbonic acid. When the analyte comes out of the column, it enters a chamber of the suppressor. Here, an ion exchange resin supplies protons, which converts the bicarbonate and carbonate anions into carbonic acid. The conversion of the bicarbonate and carbonate anions into carbonic acid solves the high background conductivity problem, since the process produces a weak electrolyte of low conductivity. Thus, using a suppressor increases the analyte signal-to-noise ratio and decreases the background signal. The sample coming out of the suppressor reaches the conductivity detector. The ions enter a flow cell containing 2 electrodes, which have a potential applied across them. As the ions pass through, a current flows. The current is proportional to the conductivity, which is related to the ion concentration. Once the conversions are complete and the analyte anions are detected, the next step in the suppressor sequence commences. In the second step, the chamber moves to its next position, where it's subjected to a regenerating solution of sulfuric acid. A proton from the sulfuric acid replaces the sodium cation on the cation exchange resin. This allows for the resin to be transformed back to its original form. Finally, in the last step of the suppressor process, the chamber moves to a third position where it's rinsed with water to eliminate unbound protons. I hope this video has been useful for you. If you have any questions, please direct them to me or your TA, and thanks for watching.